Yes. Good morning. So we move then to the reason we are studying these phase transitions, namely that they could leave some remnant, which we might say, and therefore we might be able to see to this early moment in the universe where something remarkable happens. And so now the first of these remnants is then gravitational waves. Gravitational waves are kind of an ideal probe, of course, of the early universe since they interact so weakly. So if they are once produced, then practically nothing happens to them afterwards, and we can directly see to very early moments. And now I will start somehow this discussion from a maybe a bit unlikely perspective, but let's consider first photons, so blackbody radiation. So we take some plasma with charged particles, plus, minus, so like the early universe before recombination. And so now these guys, they are then flying around with some velocities, and every now and then they can exchange photons, emit photons, and also absorb photons. So therefore, in this charged plasma, there is a certain distribution of photons. And so in fact, we could say what is the energy density carried by photons. And so this would be, well, there are two polarizations. Then there is some phase space density, T3K, 2 pi cubed. Then they carry energy, so let me write it as K, that's the energy of the photons. And then there is like the phase space density. And so now in equilibrium, the phase space density would have like a vacuum-like part plus the Bose distribution. This is the same type of combination which we saw in the first lecture. So this is in equilibrium. Okay, so now we can ask a question. I mean, these whatever electrons or positrons or whatnot, I mean, they not only do they have a charge, but they also carry energy, and they carry mass, maybe momentum. And when they scatter, then there are also movements of, well, there are accelerations. Energy flows are changing directions. And so we could ask if they also produce, question is, can collisions also produce gravitational waves? And so now, so far, that has nothing to do with the phase transition yet. It's just any plasma where things are happening. Well, the answer, and I will try to explain this, is in principle, yes. Well, yes, they do. But that radiation, so not photons, but gravitational waves, is unlikely to be equilibrium, not thermalized. You can produce something, but they are not reabsorbed, for instance. Most probably. And so let me try to explain this. And also why they do not thermalize. So let's take now a process, and I'll take, let's say, it doesn't really matter what I take, but let me take spin. Maybe it's easiest to understand if I take spin one particle like a gauge field, and I take another spin one particle like a gauge field here. If they come together, I have, so to say, spin 2. And so indeed, if you take two gauge fields, they can come together and form an energy momentum tensor. And whenever you have an energy momentum tensor, you can generate a graviton. I would denote it by oops, sort of a double line. Now this vertex is, in the Einstein equations, there is a, well, there's the gravitational constant, so there is suppression. So this is suppressed by 1 over the Planck mass. So it's a very weak vertex, but still in principle it's there. Okay, so you could say, let's take 2 spin 1 and they produce a graviton. Well, this is not allowed because you know that if these are massless particles, it is a massless particle, there's no phase space for two massless particles to go into a third massless particle. This is not allowed, but it's easy to fix that. Let me take here another spin, other gauge field, and just let it scatter like that. Now this is a perfectly allowed process. Well, there's an additional suppression here from the coupling, which I denote by G. So now let us try to estimate the rate of how fast this process happens. And so more precisely, I want to kind of consider a similar quantity like there, so, but now energy carried by gravitational waves. And I want to see what is the rate of this process. So I take the rate dt, and also it's a function of momentum of this graviton. Let me denote that by k. And so often when one looks at spectra, it's good to look at it as a function of k, and if one looks at it as a function of lnk, then it's easy to look at dimensions because lnk is dimensionless. So what I now would say is that this rate, and I will give a bit of detail in a second, looks as follows. So whenever you compute a rate, you have to take an amplitude and square it. So therefore you will have g squared, and usually it's nice to write g squared as alpha. So alpha is g squared over 4 pi. And these factors of 4 pi are not so, we are just looking at like parametric magnitude, so don't worry about the 4 pi's. But it's proportional to g squared, so alpha. It's also proportional to 1 over m Planck, but then squared, so m Planck squared. Otherwise, the process looks very similar to the photon case. So I could write d3k as, dk times k squared, and then still I take a lambda. So then in total, the dimension is k cubed times k is k to the 4th. So somehow I could put here like k to the 4th. And then I have to take the energy of this graviton from somewhere. So here now there's a small difference because this is in equilibrium, so things happen in all directions. But here I'm just looking at the production. And so if I'm producing a graviton of k, I have to get the energy out of somewhere. But energy I can always get out of a thermal fluctuation. So let me say that there is somewhere, for instance, a Boltzmann distribution of k comes from this guy or this guy. They can appear there with their thermal distributions. So something like this, and now the dimensions don't still quite match because this is GV to the 4th, and there's 1 over t here, so in total GV to the 5th, and here I have 1 m Planck squared, so I would have to have upstairs then, I'm missing somehow dimension 3, I would have to have 7 somehow. So let me put here some function coming from the thermal average of all these guys, which I denote by phi k t, and this is a dimension let's say t cubed. Okay. I just took it from here. I mean, okay, d3k is 4 pi k squared dk is 4 pi k cubed d ln k, and then I divide it by ln k, and then I have k cubed times this k, it's k fourth. Okay, so before we come back to this, let me put in some small parentheses, because I think in one of the lectures last week you saw already lots of Boltzmann equations. So if you wanted to look at this a bit more precisely, you could do a Boltzmann equation. You could say that, okay, this, let's call that momentum K2, this one P2, this one P1, this is K, So actually, so more precisely, from Boltzmann, what this rate would be is that you would have to integrate over all the momenta here, P1, P2, K2. Okay, with the usual measure, then there is the conservation of energy. P1 plus P2, these capital letters for me are the 4 momenta, and the small ones are 3 momenta. That's the energy comes in, and then K2 minus K goes out. And then there is then you would have to take the matrix element for this process and put that squared. And then you multiply by the thermal distribution. So in this case, for instance, there's a boson in the initial state, there's a boson in another boson in the initial state, and then there is this boson in the final state, 1 plus NB K2. The graviton is not thermal, so I don't put any Bose distribution there. It's just the graviton being produced. So something like that, and then maybe some other weights, some other functions here. For instance, when I'm looking at the energy, I have to weight the rate by the energy as I had it there, so some additional energy or so. So now it's a little bit more complicated, but if you now work with this, then you would be able to come back here and figure out the function phi. But for us, it's not so important now, so I will leave it like that. Oh, 1 plus, that is always in the Boltzmann equation, so that's the Bose enhancement. I mean, for fermions, there's 1 minus Fermi, that's the Fermi blocking. And for bosons, it's 1 plus, so that's the famous Bose enhancement, that if you have bosons, then the other bosons like to go there. They like to stick together. That's, it's a famous factor in the Boltzmann equation. Okay, so now what I want to do is let us estimate. We are kind of trying to see if it, under any circumstances, could happen that these gravitons thermalize. So I want to estimate the maximum of this rate. And for that, I will assume that this function, assume phi slowly varying. It is not really a very important assumption because if I look at the function, the important function is there are some powers of k to the 4th, and then there's the Bose distribution. But at very large k's, the Bose distribution becomes just a Boltzmann distribution, e to minus k over t. So very, very strong suppression at large momenta, and then some growth at small momenta. Now, even if I put some powers or whatnot in this function phi, it doesn't really change the big picture. And so you immediately see that, okay, there's a growing function, then there's a cut function, so the maximum of this distribution is somewhere where k over t is of order 1, so to say. And then the maximal value is of order t to the 4th. These are that's very rough estimates. But that's all we need. So now what I would say is that this maximum is sort of order alpha Planck mass squared times then the maximal value here, so t to the fourth times the function here, so t to the cubed, so of t to the seventh. Okay. So now I want to, this is the rate of production of gravitational waves. Now I want to, let's normalize it to radiation. Energy, density, t to the fourth. And then I can say, then I get the real rate. So this is the change of rate of the energy density, and normalized by the energy density itself, then that's the rate. And now the system that these gravitons, they would thermalize. They would thermalize if this rate is larger than what? In cosmology, the relevant rate to which we compare is always the Hubble rate. That tells how fast the temperature is changing, how fast the things are changing. It's larger than the Hubble rate, h. And h is, within the similar rough approximation, it's t squared over Planck mass. So now I get an inequality. It would thermalize if alpha t to the seventh divided by t to the fourth, alpha t cubed over Planck mass squared is larger than t squared over Planck mass. And now I can, well, I divide it by t squared over Planck mass. So I get alpha t Planck mass larger than 1, which is equivalent to saying that t larger than Planck mass divided by alpha. It's just from dimensions. I mean, the dimensions have to be, this is gv to the fourth divided by t is gv to the fifth. There is Planck mass squared here. So upstairs have to be gv to the seventh. We had here k to the fourth, and this was some complicated function which you can compute from here, but we didn't want to do. So I just said it as dimension t to the fourth. Now you say maybe it's not t to the fourth, t to the cubed. Maybe it's k to the cubed. But it doesn't matter because the maximum anyway is of order k or of order t.
What about the number density?
Number density.
Yeah, the distribution is just a number.
This one, NB. Though that I replaced by the e to minus kt. Because at large k, the Boltzmann distribution goes to the Boltzmann distribution. So it's here. That's the NB from NB. Okay, so now this looks crazy. I mean, normally if we had temperatures which are larger than the Planck mass, then surely our description would not be self-consistent. We would need some other theory of gravity or quantum gravity or something. So it's unlikely that such temperatures are achieved in the early universe. And if one has sort of, normally one looks at inflation, reheating after inflation, then the highest temperature after inflation is normally much below the Planck mass. So it's unlikely to be highly unlikely. Well, even if these gravitons don't thermalize, then some of them are still produced. I mean, these processes, they do take place. For sure, they do take place. But then you don't produce very much because the production rate is suppressed by a high power of temperature. And if you don't go up to these high temperatures, then you produce much less. Still, you produce something. So now let me draw a plot then what probably really happens. And then we also come to the phase transitions. So now is a large plot, so let me try to use the whole blackboard. And so, okay, I have here axis which is which is the frequency today, f in hertz. And here is omega GWh squared. That's the way we measure in cosmology energy densities. So this is the fractional energy density normalized to the critical energy density. H squared is one uses in tables, in Planck data and whatnot. And so let me put here some numbers. So 10 to minus 10 is kind of interesting both from cosmology and from observation, as we will see. And 10 to minus 40 here maybe. And so let me 20, 30. That's the problem always with gravitational waves. Normally you get very little, so you have to kind of have huge scales here. And then frequency, I put here 10 to minus 6. I put 1 hertz, 10 to 0, 10 to 6, 10 to 12. So now there's an important frequency here, which, if we have time, I'll explain, which is if you have thermal motion like blackbody radiation, then the frequency today, well, we know what the blackbody radiation frequency is. It's in the wavelength is a microwave. A microwave is a short distance, and this means a large frequency in hertz. And it's like 100 gigahertz. And now these processes here, which we were considering for the gravitational waves, they're really the same type of scatterings as for the photons. So whatever we do produce, even if only little, it lies in the same frequency range. So there is some kind of a maximum here, and the shape is really similar to the shape here. So very tightly cut off at large frequencies, large energies, large momenta, and then a little bit less tightly cut off at small. And so actually we do know where the maximum is. The maximum is just in the same microwave range, the photons in the microwave background. What we do not know is the amplitude. So if the highest temperature of the universe would be much larger than the Planck mass for some mysterious reason, then the amplitude could be high. Since the maximum temperature is most likely much less than the Planck mass, then we would have to scale down the amplitude, because the amplitude scales with the high power of T. And T max is now the highest temperature of T that we would get. Okay, so that's now one component, and it is for sure it is there, but whether we will ever observe it is another question. Okay, so now then there are observations of various types. There are direct observations, of course, nowadays of gravitational waves, and then there are indirect observations. And there's an interesting indirect observation which one could talk a lot about, and I don't know exactly where the curve is, but somehow, let's say somewhere here. And that is that we do know how much energy density there is in the early universe, and that is parameterized usually by this number, which is called the N effective. And N effective, it's defined such that it's sort of 3, like there are 3 light neutrinos. But then it's not exactly 3, then there are some corrections here. And if there were additional degrees of freedom apart from the neutrinos, they would contribute to this N effective. And this is measured rather precisely today and will be measured more precisely in the future. And so if we had something else than the usual standard model particles, they would contribute to the N effective. Also, if there would be very many gravitational waves, lots of energy density in the gravitational waves, at some point we would see them in the N effective. That's one constraint. Okay, then there are many other, well, there's LIGO, Virgo. Now what's very interesting for cosmology is then is this LISA. Okay. The space-based interferometer for gravitational waves, and it's somewhere here. the frequency is less than 1 hertz, that where it's the most sensitive, and the amplitude maybe 10 to minus 10, maybe a bit below. Maybe I should have, maybe 10 to minus 12 or so. So now you see that this kind of background, which we know that is there, but maybe very slow, it's very, very far from what LISA is doing. It's in a completely different frequency range, and here there are orders and orders of magnitude in between. So now we come to the phase transitions, because it's kind of an accident. It really is a complete accident, but it so happens that if we have a phase transition in the Electroweak sector, so with something to do with the Higgs, not in the standard model, because there we don't have a transition as we've seen, but in some extension of the standard model. Then by some miracle, which maybe I can explain, the frequency is precisely where the LISA is. I mean, LISA was not designed to look for these phase transitions. It was designed to look for some astrophysical things, like in spirals and whatnot. But by then, phase transitions, some signal here, which maybe goes close to the LISA. So that's what makes it so exciting. LISA will be flying, I don't know what, maybe 15 years or maybe even a bit less. And so today, lots and lots of people are writing papers about electroweak phase transition in various cases and hoping to get a signal which would overlap with the LISA sensitivity signal. Of course, there are many other things then also in planning, maybe even more sensitive things further in the future, but that's then so far in the future that let's not even think about that today. Okay, so now this is a very important picture to have in mind. So let me still somehow maybe like give some explanations of some of these scales, why they are where they are. Well, so scales are always difficult to estimate because one has to put in some like real numbers. But okay, let's start with this. This is a very important. Let's start with that. So okay, so what is the f of? So f of, let's say f of t. So if we had a thermal component, thermal radiation, what is its frequency today? So frequency is omega over 2 pi. So I write it h bar omega over 2 pi h bar. And now h bar omega, that's the energy. So now I put here the frequency we have today is the cosmic microwave background. It has temperature 2.7 Kelvin. So I put it there. 2 pi. Now h bar, now we need h bar in some units, and a simple way to write h bar, it's about 7 times 10 to minus 16 electron volts second. Now, one thing to remember is that 1 electron volt is 11,600 Kelvin. So therefore I can write Kelvin as 2.7 electron volt divided by 11,600 and then 2 pi 7 10 to minus 16 eV second. Okay, so now eV cancels against eV, And let's say 2.7 is very close to pi, roughly speaking. 2 times 7 very close to 10. This is like 10 to 4, 10 to 4, 10 to 5 times 10 to minus 16, 10 to minus 11. So out comes 10, and then I put it upstairs. So 10 to 11 over second. So 100 times 10 to 9, 100 gigahertz. So that's now this one here. That at least one can understand. Okay, so now more important but less trivial is the frequency of the electroweak phase transition. So now let's first of all, let's define the LH is the length of horizon length of horizon. At electroweak epoch. So actually I defined this as the inverse of the Hubble rate. So m Planck divided by T electroweak squared. And temperature of the electroweak phase transition is of order 100 GeV. We saw it on some plot the other day. But this is the horizon at that time, at the time of the electroweak phase in the early universe. Now the question is, what is that horizon today? So we have to scale it to today. So that horizon today is what is that horizon at that time, and then we have to scale it by the expansion of the universe, and I denote by A the scale factor, and so we have to put here A today, and today is the CMB 2.7 Kelvin. A today divided by the electroweak. That's the relative expansion. And now the scale factor is roughly speaking inversely proportional to the temperature. So well, there are one talks about entropy conservation in the early universe. There is some additional factor related to the number of degrees of freedom, but this is kind of a slowly varying function. So roughly speaking, it's temperature. So this is like T electroweak, T CMB times m Planck T electroweak squared. So m Planck, one of the T electroweaks cancels, CMB. So now Planck mass 10 to 19 GeV, CMB 3 Kelvin, and we know that 10 to 4 Kelvin is electron volt. So 3 Kelvin is like 10 to minus 3 electron volt. Electroweak is 100 GeV. Okay, electron volt is 10 to minus 9 GeV. So I get in total 10 to minus 12 times 100, 10 to minus 10, and then I put it upstairs, so I get 10 to 29 GeV. Now I want to convert it somehow to meters. And yes, sorry. Thanks. The good rule to remember is that GeV times Fermi is 5. So therefore, 1 over GeV is Fermi divided by 5. And that is, Fermi is 10 to minus 15 divided by 10, roughly 10 to minus 16 meters. 1 over GeV is like 10 to minus 16 meters. Okay, so 10 to minus 16, so I get 10 to 13 meters. And how much time does it take to go to 10 to minus 13 meters? Well, speed of light is 3 times 10 to 8 meters per second. So sort of 10 to 9, let's say. So it's like 10 to 4 seconds. 10 to 4 seconds, and therefore frequency of electroweak horizon today is like 10 to minus 4 hertz. But the physics that we are interested in is inside the horizon. Inside the horizon, it's shorter wavelength. It's shorter wavelength, it's larger frequency. So causal physics within the electroweak horizon, shorter wavelength, larger frequency. And so it is, the factor is typically about 100. Maybe I have time to explain that as well. And so something like in the 10 to minus 2 hertz is what people often consider. And so that's the accident now. It really happens to be here in the 10 to minus 2 hertz range that this frequency peaks. So that's B. So now we understand sort of this FK horizon of electroweak. That's the B, and that happens to be here. Okay, so one more important thing. I mean, the litho sensitivity, this is, I think, too difficult for theoretician to understand, so let's not even try that. But what I could say why some people think that that one could get somewhere in that range. It's the third, so somehow the amplitude of that peak. Okay, so let me just write. Okay, let me write here some formulae, and then I try to explain what it is. So there's some numerical factor which is not well known. It must come from some simulations or so, but maybe 10 to minus 5. But then there are two factors which one can kind of understand. And one of them is that now if we want to generate gravitational waves out of some dynamics, this means that we have to take part of the energy in this dynamics and convert it to gravitational waves. This omega is the ratio of the energy density in gravitational waves to the other energy density. So therefore, in this omega, there must be a ratio of what is converted to the total. And what is converted is exactly what we already had. It's the latent heat. That's the energy that is released in a transition. So if we had maximal efficiency there, we were able to convert all of that energy into gravitational waves. Then we would convert the fraction of L over energy density to gravitational waves. This is the absolute maximum. That's part of the reason why there is some small number here, that the efficiency, you will never convert everything to gravitational waves, but you convert something. And now everything must appear in a square. This is like a bit like in the Boltzmann equation, but and also one can see it in another way, to which we will come back in the second half of today's lecture. But always, this is kind of the amplitude, and then it comes as a square. That's one factor. And then there's another factor, which is that, as you also heard in the, well, I think as you know very well, I mean, gravitational waves are not easily produced. You have to have these quadrupoles. You have to break enough symmetries to produce gravitational waves. And so then there is some kind of scale which tells how efficiently you are breaking symmetries. And this scale is, often one writes it as LB over LH. So LH was the horizon length. And now LB is the bubble distance. Sort of this, as we discussed yesterday, you nucleate these bubbles, and there's kind of some typical distance scales at which you nucleate. And that somehow sets some sort of a geometry. At which geometry do you break rotational symmetries or so? And then it also must be squared. So now then we can estimate this. So from nucleation computations, we just sketch things yesterday, but this is one of the basic quantities that people then estimate, is this ratio. And so one finds, let's say if one pushes to a transition where there's a very large surface tension, then it's difficult to go through the transition. Well, you can make a transition somehow very, very violent, and so sometimes one can go up to 10 to minus 2, but more often it's a bit smaller, maybe 10 to minus 3. But let's be optimistic. Let's say we could get distance scale 10 to minus 2. Now, then what is L over E? It is somehow from counting degrees of freedom. So for instance, if we have a phase transition where the Higgs field undergoes the phase transition, then the other fields are kind of spectators, and the energy you release is somehow also coming from the Higgs, essentially. And Higgs is one physical degree of freedom. And in the standard model, there are in total like 106.75 or 100 degrees of freedom. So Higgs is just 1 out of 100. And so that's the typical, that's what you would expect for the latent heat to be, also 10 to minus 2. This would be sort of the naive estimates. And if you now put those in, then you get 10 to minus 5, and this is from simulations, 10 to minus 5, 10 to minus 2 squared, 10 to minus 4, 10 to minus 2 squared, 10 to minus 4, so minus 8, minus 5, 10 to minus 13. So pushing everything a little bit, you get 10 to minus 13. And so 10 to minus 13 is a small number, but still it's not so small. It's somewhere here. And Lisa, maybe 10 to minus 12. Well, so we are close. And so the only thing that needs to happen is that there's a miracle of one or the other sort here, that for some reason the transition is much stronger than we estimated here. That, I don't know, half of the energy density is converted to gravitational waves, or the transition happens in a very strange way, not in these nucleations that we are familiar with, but with something else, so that the distance scale is different. And then we could be in business. Okay. So I think that's for the overall picture, and in the next lecture I will then try to again go a bit more into detail and show how one could really then try to compute this, not only arguing but like really compute it. I mean, ultimately from simulations, but at least to have some formalism for how we could do that. So let's take a break till 10, and then continue. God. So therefore, to define the quantity, one should take some average over the wavelength or so, and this makes actually the GR derivation, in some sense, delicate. So now what I will do is I will present a completely different type of a derivation, which is basically quantum mechanical. So I'm kind of taking the gravity, I'm not quantizing gravity as a whole, but I'm quantizing gravitons, so small fluctuations around the background. And it turns out, in some sense, this derivation is it's simpler because you don't need to argue. On the price you pay is you have to believe that you can quantize these gravitons, these small waves. That's the price, but the good thing is, so it's simpler, and also there's, in this derivation, I will kind of do it rather generally, so it's kind of a very general derivation. So actually it applies not only to the, so up to some point, it applies not only to the gravitational waves, it applies also to all other kinds of particles you can produce in the universe. So exotic particles, so I don't know, like sterile neutrinos or maybe dark matter, some forms of dark matter. So it's kind of simpler, and it's kind of general. So that's why I think it's nice to have seen it. So really, what I'm doing now for a while is just quantum mechanics, sort of time-dependent perturbation theory in quantum mechanics. So we start with some Hamiltonian, and we think that the Hamiltonian has parts which describes particles in the plasma. Then there is some part which describes like the free propagation of our gravitons, and then there is an interaction part. And now I will assume, and I will write this quite generally, I just assume that the interaction part has the following form, that there is some small coupling epsilon, so much less than 1. And then Hamiltonian is an integral over space. And then there are two kinds of operators. There's what I denote by h hat and then j hat. So the essential thing is there's a linear coupling of my field. In this case, the h hat is the graviton. And j is then some operator containing the plasma particles. In the previous plots, for instance, the gauge fields. So in the graviton case, this would be the T mu nu. But I write it more generally also because J is simpler to write than T mu nu. So, but this is the form that T mu nu couples to gravitons at linear order in small perturbations. Okay, so now what we are interested in is a transition matrix element. So in time-dependent perturbation theory, it is, well, let me denote it by TFI, from some initial state to some final state. So we take matrix element, initial state, final state, and then in between there is an integral of the interaction Hamiltonian. Okay, so this is the matrix element. Then we have to take the matrix element squared, divide that by time to get the rate, and take some limits. Okay, so how do we do that? Well, so now what we do is the following. I write the initial state as saying that the initial state has 0 gravitons, and then it is some initial state of the plasma. And then I write the final state as a state which has 1 graviton of momentum k, and then some final state of the plasma. So here I have now integral over time, and here there was already an integral over x. So this is now epsilon times then integral over, I put a capital X prime, integral over time and space. And then the graviton field and the J. And now what I do with the graviton field is I say that this is like a, well, it's like a plane wave. Okay, okay. So very good. I forgot to say it. I'm now for the derivation. For a moment I'm operating in a local Minkowskian frame to keep things simple. Later on I will say something about curved background. So in local Minkowskian, this is what we learn in well, in field theory maybe. Plane wave has two parts: annihilation operator and creation operator. Okay, so now what you see is that, I mean, this annihilation and creation operator, they operate on this part of the Hilbert space, on the part of the Hilbert space where the gravitons live. And of course, if an annihilation operator operates on the vacuum, it gives nothing, zero. It annihilates the vacuum. So I get something if I take K and the creation operator and the vacuum. And this in fact is simple because this state is nothing but, I mean, K is the creation of K operating on the vacuum. That's the K. So the conjugate is 0, a K, a dagger Q, 0. And now I can write this as a commutator plus I've added something I subtracted something, I have to add the same thing. Plus AQ dagger AK. But that gives nothing because that, again, the annihilation is on the right hand side, it annihilates the vacuum. Whereas this commutator is delta 3 K minus Q. And so therefore my TFI becomes, okay, it is epsilon. Then there's the integral over x prime. Then I have from H and this matrix element, the Q gets replaced by K. So I have 2 pi cubed 2 times EK and e to I k dot x prime. Now I think I've dealt with the part of the matrix element which comes from the graviton, and then left over is the part which comes from the plasma particle. So Fj I. Okay, good. So now what we need is following. Some production rate. So in fact, this production rate is the rate in phase space. So F is like a phase space density of producing gravitons of momentum k, okay, vector, and so rate of that. And in phase space, there's often a factor 2 pi cubed. So it's sort of like this. So what I now need is the following: that I would like to take this amplitude TFI, but then I need to take the amplitude squared, and then I take the rate so rate is per time per volume, T over volume. I want to send T and V to infinity, and then I need to average this because this production takes place in a plasma. So I have to average this. So I have to sum over all initial states with their energies and normalized by the partition function. That's the probability of finding some initial state, and from that initial state I can produce with this amplitude, and then I normalize, and that should give me the rate. So now let's try to write then the square of this amplitude. Well, so square of that amplitude is epsilon squared 2 pi cubed 2 times the energy. And then there's an integral, but now I have, if I take a square, I have two integrals, x prime, y prime. And then once I have k dot x prime, and then from the complex conjugate I get minus I k dot y prime, and then I have f j x prime I, and the complex conjugate amplitude I j dagger if it were a complex operator for generality f. Let me simplify this a bit by taking that out and putting here x prime minus y prime. Okay, so now the following trick. There are two integrations here, but we are assuming that the space, we are in a Minkowskian space, so then space is homogeneous, I mean translationally invariant in all directions. So I can substitute, I can put here x prime, let me write x prime as y prime plus x. So I'm taking a new integration variable x. And however then, all kinds of expectation values, like this one, if I write x prime, it's y prime plus x, I j dagger y prime f. The translational invariant, so the y prime appears in both positions, so I can just eliminate the y prime. It changes nothing. I've just transferred the whole system somewhere, but who cares where the system is? So then I can eliminate the y prime and take the j dagger at 0. Well, that's very convenient because this means that the integral, and here the same happens. I put x prime is y prime plus x, so x prime minus y prime is just x. So again, there's no dependence on y prime, and that means that the integration over y prime is just the overall factor, and that's exactly what we need, because here we also have the overall factor of the space-time volume. So the integral over y prime is then just over the space-time volume. And then we are left with this, but now what I do now next is, and this is sort of important as long as we're in quantum mechanics, we have to pay attention to the ordering of things. And I want to put the initial state now on the left. So then I have to put the j this term. This is a complex number, so I have to. As long as I have matrix elements, everything is fine. They are just complex numbers. I can order them as I wish. So I put that on the left, and jx on the right. Good. So over x, yes, very good. Thanks. There's an integration over x, and the Fourier factor here as well. this is like the phase space density. So, you know, in phase space you have phase space density is usually a function of momentum and position. But now I'm assuming that everything is homogeneous. So no dependence on position, but still dependence on momentum. And then f dot is time derivative thereof. Time derivative of phase space density of, in this case, gravitons or whatever weakly interacting particles you are interested in. Well, you may ask why like 2 pi 3, but I mean it is the phase space density. It is like it's the probability of finding these particles, and the probability is you take in the initial state you didn't have any. Now we computed the transition matrix elements of producing something. That's the amplitude TFI. Square of that's proportional to probability. But now we want rate, and we want per volume. So that's why we divide by these. That's now probability divided by time by volume. That is a rate. And then we take a thermal average, because the initial state is not fixed. It can be anything. Any state, all states have to be accounted for. And that's why we take then a thermal average thereof. If we didn't have any weight here, the average would be 1, because the sum of the e to minus beta is the same as z. So that's the thermal average of a production rate. That's what it is.
I was just confused because why we are computing the matrix element rather than the transition amplitude with the U evolution operator.
Oh, you could do, I mean, I'm just trying to take, like, of course, the shortest possible way here now, so I'm maybe simplifying this and that, but at the end of the day, and we are also computing everything to leading order in this epsilon. This is some very small number. So to leading order in epsilon.
Okay, so you expanded U as 1 plus.
Yeah, to leading, exactly, to leading order in epsilon. But to any order in the interactions of the plasma particles, there I didn't make any assumption. Okay, so now, therefore, okay, what we see is that this 2 pi cubed stay nicely cancel from what we need and what we have here. And then the T times V also nicely cancels. And then we have the thermal average. So we are done, basically. F dot is epsilon squared 2 times energy. And then this guy, and okay, I was sloppy. I think I was sloppy upstairs. Maybe I was sloppy also somewhere else. I forgot to say that, I mean, here we have the initial state, but we also have the final state. So we sum over all of these. I mean, we sum not only over the initial states, but also over the final states. We sum over everything. Every process which is allowed by the matrix element, it does take place and has to be summed over. It's only the initial states which we know that are thermal. The final states, we don't know anything about them. Gravitons take away energy, so they don't need to be any more thermal. They are what they are, but we just sum over them. It's kind of an, inclusive, extremely inclusive rate. Everything is summed over. And so what then happens is, well, when you sum over the final states, then this FF is just unit operator. And the initial states, now the reason I put this on the left and this on the right is that there's the thermal average. So the initial state turns into sum over initial state with the Boltzmann weight, it turns into a thermal average. I could write here again T, but as I said in the first lecture, we leave it out. And so we just have a thermal average of one operator and the other operator. And again, I forgot the Fourier. Okay, so this is the expression I wanted to derive, and now these kind of expressions, these are kind of very basic building blocks of quantum field theory, well, also of quantum mechanics. This was basically quantum mechanics, but more generally of quantum field theory. This function one calls, well, one denotes it by, well, it's some g, Green's function, and then x is on the right-hand side. So now we are in quantum mechanics, and there ordering plays a role, and if x is on the right-hand side, we call this g smaller. It's a function of k, and this is called a quantum field theory. It's called a Boltzmann function. And so really somehow, if you study kind of mathematically rigorous quantum field theory, then one always defines different types of Boltzmann functions, and this is one of them. But so the nice thing is it's really, yeah, it's quite general, this formula. So now we want to apply it to application to gravitons. And this means that we have to replace these things with the correct things. And so epsilon, well, if you really treat these gravitons as quantum mechanical fields, then the epsilon, the small number, one has to figure it out from the Einstein equation. What is the correct normalization? But the correct normalization is square root of 8 pi divided by Planck mass. And then the J, what is the J? Well, the J is now the energy momentum tensor. But then in some polarization state, some transverse traceless physical polarization state, it's a polarization vector. And then we have to also weigh this we have to, well, okay, so let's try to put in some things here. So, okay, it's not just this 8 pi m Planck squared. Then we have from there, then we have the 1 over 2 times ek. But then we have to weigh this again with the energy, because now we are not considering the number density of the gravitons that are produced, but the energy density. That's the physical observable. So we have to weigh it by the energy. And then there's the operator. And so now there are two terms, and if I replace them, and I can sum over the polarizations, then I have once I have the Tt mu nu, and then I would have Tt dagger rho sigma, and I would have some Green's function now of the T rho sigma mu nu smaller, something like that, and then I'm okay from the phase space. I'm missing here 1 over 2 pi cubed, because that always appears. D3k over 2 pi cubed is always what appears. Now if I divide by that, I would have to put 2 pi. Anyway, this is just some prefactor. 1 is 8 cancels, so I think 1 over 2 pi squared m Planck squared. One sees how the rate is suppressed by the Planck mass, and then this is this 2-point function of k. Okay, so that's now what one would have to compute. So now let me give some, to make it a bit, this is kind of a little bit abstract still, so let's make it a bit more concrete. So some remarks on this. Okay, first remark. This sum, actually, it's very much what you've seen last week. Well, it is exactly. This is some projection operator on transverse and traceless modes. I would call it L projection on rho sigma mu nu, but it is what you've seen with which is then some other projections. And it's not so important. Somehow some indices. Yeah, let's not get. But it's exactly what you've seen before. So if you produce something out of the energy momentum tensor, then the physical waves they are produced onto the transverse traceless modes, and it comes from this polarization sum, and one can write it explicitly. And it's exactly the same as well. It's always the same. So it's what you have seen. Okay, then there's sort of this second remark is more like in parentheses. This is not really important for us, but I was saying this is a very general formula, and so in fact one can there are so many Green's functions. So this Weidmann function one can write then also in a form 2 times Bose distribution of k times imaginary part of a retarded Green's function. And the reason I want to mention this, even though only in parentheses, is that if one writes it in this way, then actually the physical interpretation is more clear, because one sees here the Bose distribution, that's where the energy comes from, energy for graviton. And then one sees an imaginary part of something, and that's one knows from scattering theory. There is this optical theorem which says that the matrix element squared is the imaginary part of, is the imaginary part of something. So this is like in the optical theorem. Imaginary parts of some amplitudes give the amplitude squared, the physical process that we are interested in. Okay, but now more importantly, we are interested in, so for these phase transitions now, we are interested in modes with where the k, the momentum is much less than temperature. You remember in the plot, there was the thermal scale here and then the physical scale much below it, the modes within the horizon of the electroweak, many orders of magnitude. So very small momenta, very large wavelengths. There are very many quanta here, and these kind of fields, very deep in the infrared, they are classical fields. If you have classical fields, then you don't need to care about all these issues with operator orderings or so. And that's, of course, what one expects. Also in GR, if you have general correlation functions of the energy momentum tensor, you don't care about the ordering. It's just a classical real number. So in fact, also, if we were to evaluate this, what we would do is we would then represent the energy momentum tensor in terms of the degrees of freedom which are important for the phase transition. And what are those? It's in fact exactly the same degrees of freedom which we briefly discussed yesterday at the end of the lecture. So it's this hydrodynamic degrees of freedom in terms of local temperature, local flow velocity, and then some order parameter, our Higgs field, for instance. So what it means is that T mu nu is then T mu nu plasma plus T mu nu of the field. And now the details are not so important, but for instance, T mu nu plasma is probably something that you have seen. So there's a part which goes like E plus P, the flow velocities, the ideal hydrodynamics. Then there is minus eta times P. This is what one calls ideal hydrodynamics. And then there are further terms with gradients, velocity gradients. This ideal hydrodynamics contains energy density and pressure as variables and the flow velocity. These velocity gradients, then they concern, there are functions there which parameterize velocity gradients. At first order, these functions are called viscosities. There are two types of viscosity, shear viscosity and bulk viscosity. They completely parameterize the first order, but in principle it's kind of like an effective theory, so you can also add, you could add further gradients. But for the studies of the electroweak phase transition, for instance, one doesn't really need to, this ideal hydro is enough for all practical purposes. And then the field, well, the field is just the field. So there you can take the textbook energy momentum tensor of a scalar field, which is d mu phi minus in my metric convention d alpha phi over 2. That's for the, okay, this would also be a term from the potential. Actually, the potential one should put here in the pressure. If phi carries free energy density as a potential, it should appear as part of the ideal hydro. So these are now very concrete. Okay, and of course, in principle, yeah. Well, that's enough. So now, so then you take these and you start simulating your hydrodynamics. You nucleate bubbles. Bubbles create temperatures. They create flows. Flows create energy momentum tensor. Gradients of the fields create energy momentum tensor. You compute your energy momentum tensor, and you put it in that 2-point function, which I've already lost, and you measure with some simulation. So maybe now one point still, because we were in, for the derivation, we were in Minkowski space. But this could be generalized. Actually, for the electroweak phase transition, it's usually not so important. Because, why is it not important? Well, because this LB, the bubble distance scale, is much less than the horizon scale. And so what you simulate is normally you don't simulate you don't simulate the whole universe. You don't even normally simulate the whole Hubble radius. You take a snapshot, a small snapshot where you have some bubbles, let's say a few bubbles, and then they collide, and you look at what happens there. But those distance scales are much below the horizon, and if you are at distance scales which are much below the horizon, then it is Minkowskian physics. And so normally for these simulations, you don't need to care about the expansion. In some other problems in cosmology, maybe inflation, reheating, or so expansion happens, relatively speaking, faster, and you would need to care about it. But if you wanted to care about it, actually you could do exactly what we did. Well, you could do more or less what we did yesterday. So yesterday we had we considered the 2-point function of the scalar field, and similarly, one could consider now the 2-point function, for instance, of the metric perturbation. and one could write it in the same way as we wrote yesterday, as some integral. And now you would have then some retarded Green's function, which takes you from the observation point to the source, or vice versa, from the source to the observation point, and then you would have the 2-point function of the sources. But these Green's functions, that's what tells you how you go from one place to the other. So these could be, it would be easy, maybe not easy analytically, but at least easy numerically to evaluate. It would be easy to analytically determine the Green's function in an expanding background, including whatever expansion you have, and then maybe carry out the integrals numerically. It can be done. The expansion can be included here. And then, okay, as a last point then, result of simulation. So let me just plot what they then normally see somehow. Of course, simulations have it's a bit always difficult with simulations because somehow as end users we tend to trust the people. When the people say, well, we did a big simulation, when then we think, oh, since it was so big, it must be good. But in the simulations, there are always their own uncertainties. There are some approximations one makes. There's some grid of so and so many points. There's a volume, which is not infinite. And with the equation of motion, one may do some approximations to make the system stable. So it's very difficult to be exactly sure that things are under control. But hoping that they are, then what people then plot is, again, one plots this omega GV, fraction of energy density in these gravitational waves. Usually people like to make it look a bit larger, so they divide away some of the factors that suppress things. For instance, often they divide away this. One of the factors that we saw was 10 to minus 2 squared, 10 to minus 4. But if you divide it away, then maybe you get something more. But 10 to minus 10 is always what one sees. That's kind of the typical scale. Okay, then you nucleate some bubbles, let them grow, let them collide. There's complicated motion. All the time you measure, then you take a Fourier transform. You get the result as a function of k. And also k, now usually to get it dimensionless, let's say you put it as a function of k times then this distance scale. This is dimensionless momentum times distance. And so then there are plots. So I don't know, then. And then there is some numerics there. Numerics is never perfect, there is some curve. And then people debate whether they can understand numerically or analytically what the power here is, what is the decay here, and of course, most importantly of all, what's the amplitude here. And this is then the tip of the plot we saw in the first lecture. Okay. So that's more or less the story. So I mean, this kind of simulations, they are nowadays big business. But I mean, what is simulated is not complicated. It's really these 2-point functions of the energy momentum tensor. And as always, with simulations, the real hard challenge is to have the systematics under control. And the systematics is not fully under control today because one is looking at a very small snapshot of the whole volume. But things will improve there. But still, it's an exciting and important topic. So I think I will leave it at that for today. And so then tomorrow we go to two more things, with this baryogenesis and magnetic fields. Baryogenesis is, in some sense, is the one which has been studied most for the electroweak phase transition, and it's maybe also the most complicated. So therefore, we will not do all these complications. We will just take some small part there of which I want to explain, and in particular, this that gives me an opportunity to do a very nice and exciting computation. So we'll try to do that tomorrow. Okay, any questions now?
For these bubbles, you mentioned that you usually
Well, I mean, in half of the if you have distance scale 10 to minus 2, then in half of the Hubble volume you would have 10 to 6 divided by 2, so 10 to 6. But if you look at the simulations, what you see in the simulation is sort of by eye, I would say you see normally like 20 bubbles if you are lucky. So it's really a very small snapshot of the full Hubble volume. Well, at the end of the simulation, all of them, I mean, that's really, the growth is really the beginning. And one of the results from these simulations is that they say that the biggest amount of gravitational waves is not so much from the initial collisions, but it's more like from this very complicated motion which comes afterwards. Lots of sound waves going here and there for a long time. It takes a long time for the sound waves to attenuate. And so there is kind of this very noisy medium for time, and that's what then produces most of the gravitational waves. Yes, it was there before, and I briefly answered it at the beginning of this lecture, but I don't know if there was no reaction, so I don't know if they heard it, but yeah. Good, thanks.